Okay, so why don't we get started? I know our speaker's ready. So I'm Roger Wakimoto. I'm the Vice Chancellor for Research, Innovation, and Creative Activities. I want to welcome you to the 140th Faculty Research Lecture. A little bit of housekeeping. The format is going to be a presentation. We also are going to have plenty of time for Q&A, which will be facilitated. Ask, as I always do, please silence your phone. It can be very disruptive to hear a phone go off in the middle of a presentation. And also that the lecture will be recorded. So that's primarily, for me at least, it's primarily for those who can't make it. There's always people that have conflicts but really wanted to hear the lecture. So it's being recorded. It'll be posted on my website so those can view it later. And then, oftentimes during the Q&A, we will have microphones. Please wait till the microphone comes to you. I know people yell that my voice is loud enough. That isn't the issue. If you don't have the microphone, your question isn't going to get on the recording, and so no one will hear the question. They'll hear his answer, but they won't know what question was being asked. The only other thing I'll say before introducing Darnell Hunt, you may have noticed today in your inbox that Stratcom released an interview with our speaker. I wanted to pull out a couple excerpts about what he said about today's talk. The first quote is, "The universe is amazing, really beautiful and fascinating and surprising, and a sort of a source of inspiration and intellectual stimulation." He goes on to say, "I want people to appreciate that this is not a secret society. Everyone can and should understand this at some level. In principle, this would be something that everyone should be able to participate and appreciate, kind of like we all appreciate a work of art." So I thought those were very nice words to share at the beginning here. And now with that, it's my pleasure and honor to introduce our Executive Vice Chancellor and Darnell Hunt to make the official introduction to our speaker.
Thank you, Roger. Good afternoon. I'm delighted to join you today for this honored tradition. For over a century, we have come together to celebrate the scholarship of our colleagues, the questions they raise, the illumination they provide, and the intellectual community they reaffirm. Tommaso Treu is Distinguished Professor and Vice Chair for Astronomy and Astrophysics in Physics and Astronomy Department. And we are honored to have him deliver the 140th Faculty Research Lecture, "What is the Universe Made of?" Professor Treu holds a PhD in physics from Scuola Normale Superiore in Italy. His research interests include fundamental physics and cosmology, galaxy formation and evolution, and supermassive black holes. It is fitting that we come together to hear Professor Treu a mere 2 weeks after Artemis II brought the attention of so many back to space. The excitement over Artemis II recalls 1968. At the end of that tumultuous year, a message of goodwill from Apollo 8 astronauts bearing witness to the beauty of Earthrise from lunar orbit reminded the world of what connects us as human beings. Similarly, during another tense time, Artemis II just graced us with a reminder of the power of peaceful collaboration and how science can elevate all. I think it is fair to say that the work of Professor Treu is similarly exciting. His work sheds light on the formative history of this vast cosmos we are privileged to live in. The insights of Professor Treu is helping discover about the development of supermassive black holes, dark energy, and dark matter evolution, and gravitational lensing are important to scientists, to be sure. But they are also of interest to poets and philosophers, novelists and artists, and anyone who wonders how the universe became what it is, and anyone who holds steadfast to the conviction that we can know more today than we did yesterday. Professor Treu's accomplishments provide ample evidence of his academic prowess. The Newton Lacey Pierce Prize of the American Astronomical Society, the Newcomb Cleveland Prize of the American Association for the Advancement of Science, exciting discoveries using both the Hubble and Webb telescopes, service on the advisory committee of the planned 30-meter telescope, and more. Just as important, if you talk to his colleagues, you are likely to hear terms such as warm, helpful, level-headed, and wise. That is an impressive cluster of qualities. We are fortunate to have such a scholar and colleague among us. I am pleased to invite Professor Tommaso Treu to deliver the 140th University Research Lecture. Thank you.
Yes, I am indeed warm, about 97 degrees Fahrenheit. Okay, so what the universe is made of is a question I've been asking myself ever since I can remember. At some point growing up, I realized this is a question that humans have been asking since the beginning of time. Not only I was not alone in this pursuit, but asking this kind of questions is one of the distinctive features of being humans. Seeking answers to this question serves no apparent purpose, and yet I would argue that unfettered curiosity is perhaps one of the key ingredients of our evolutionary success as humans, and one of the foundations of our civilization. It is certainly at the core of the mission of this great university. As far as I can tell, artificial intelligence does not show pure curiosity, although that name may come. In my opinion, that is the ultimate Turing test. Before I begin, I would like to thank my colleagues in physics and astronomy for nominating me, but most importantly for making the department a stimulating and supporting environment. It is an honor and joy to work with them. I would also like to thank my mentors, Massimo Stiavelli, Richard Ellis, Matt Malkin, Alan Dressler, Roger Blanford, and Giuseppe Bertin, from whom I learned so much. And last but not least, I would like to thank my wife, Professor Stefania Tutino. And there are many reasons for me to be grateful to her, but the one that is relevant in this context is that, like no other person I've ever met in my life, she has the ability to make me see the world in a different way. And as you will see, a central theme of my talk is that sometimes what you believe to be true turns out to be wrong and needs to be replaced by an improved understanding. Being open to this possibility is a necessary condition for discovery. All right, let's get into it. So what is the universe made of? So I want to take a little step back and tell you why I think this is a useful pursuit. The first one is that we need it. If you see any child, they will have lots of questions. So curiosity is a feature of human beings, is a necessity. There's even a name for it. It's called epistemophilic instinct. It's similar to the instinct to seek food, love, but also the instinct for knowledge. The second is discoveries. Pure curiosity leads to these accidental discoveries. And this very question that I'm asking, what is the universe made of, led to the discovery of the atomic structure and electrons and powers electronics. Everything you see today, the screen, your cell phone, this would not have been possible without someone at some point asking what is the universe made of. And the third one is meaning. When we ask these kind of questions, in some sense, we're trying to give meaning to our life. And it's similar to art in some sense. We try to find out what there is to it, why are we alive, and asking what is the universe made of is one of those questions. There's also another reason I think is particularly timely now. Science keeps us honest. So if I make a measurement or I have a theory, someone can repeat the measurement and prove it to be wrong, or someone can disprove my theory. And this is a core foundation of our society. I won't butcher this sentence, but I'll try to read it in the best possible way. This is a beautiful sentence from The Origin of Totalitarianism. And Hannah Arendt said, "The ideal subject of totalitarian rule is not the convinced Nazi or the dedicated communist, but people for whom the distinction between fact and fiction, true and false, no longer exists." So science is a foundation of our society. And before I really begin, I want to thank my students and postdocs. There's a list of them here over many years. I've been privileged to mentor all these young people. The ones in yellow are currently at UCLA, and it's one of the greatest joys of my professional life to see them grow from students to scientists. So let's start from the beginning of history, or close to it. This is a picture from Raphael's The School of Athens in the middle. You can see in the middle the School of Athens, there's Aristotle and Plato, and they're discussing something about Earth and the heavens, Earth and space, Earth and the sky. And at that time, one of the prevailing theories was that Earth was made of 4 elements: fire, wind, water, and earth. And importantly, space, or the sky, the solar system, whatever you want to call it, was a distinct thing, was a different thing, made of something else that they used to call ether, a completely different substance. And this substance was supposed to be perfect, as opposed to the imperfect world we live in. And as you can see, this idea has been popular through the ages. The 5 elements of yoga, if you Google it, for example, is pretty much the same as Plato and Aristotle were saying. So this is a pervasive idea in our society. There was another important term that we should come to know, this other idea by Democritus that introduced the term atoms. According to Democritus, the universe was really made of little things that he called atoms from A, temno, cannot be broken. And those atoms getting together would make all kinds of substances. Now, from a physics standpoint, this is not correct. This is not the correct theory of how we understand things, but the name stuck. So it's very important to keep this name in mind. Now we'll jump forward a few centuries to modern physics. And this is something that I hope most of you have seen. This is the periodic table of elements. Raise your hands. Have you ever seen this before? Okay, good. No, you'd be surprised. Okay. Okay, so this is a brilliant achievement. So at some point, humans discovered that everything they could interact with was really made of a finite number of objects that they called atoms because they could not divide them further, and they had distinct chemical properties. You see, it's a fairly large number. It's about 100, give or take a few. But this describes all the chemistry that you have. Describes molecules, atoms, water, my shoes, what I had for lunch today. Everything can be described by this. Now, we now know that this is not really the end of the story. If you can zoom in into an atom, like this one, the atom itself is not really an atom. It has an internal structure. It can be further divided. And let's assume that I scale up an atom to the size of this room. Most of the volume in this room will be occupied by the electrons. The electrons are very light particles that occupy most of the volume of the atom. Most of the mass, the weight of the atom, is in what we call the nucleus. And if I scale the atom to this room, the nucleus is about the size of my hair. I don't have many left, but you can think about them as nucleus. And the nucleus is really made of other particles. Those are protons and neutrons. And kind of like in a Matryoshka's picture, the protons and neutrons further subdivide into quarks. They're called the up and down quarks. So this is the current picture of atoms. And atoms bind to each other by sharing electrons and doing things like that. So this is what we use to understand, for example, chemistry or these sort of things. So our current view, this is all the stuff that is in atoms, can be summarized by 3 particles. So we've gone to about 100 to 3. So that's pretty good. See, this is a little secret. So physicists have very short memory. So we try to simplify everything. Ideally, we would like to have one equation that describes everything. We can't quite go there, but we reduce the number of particles as much as possible. And so there's 2 quarks. They're called up and down, and 1 electron. Unfortunately, this is not quite enough. Turns out that if you do experiments in big laboratories like the CERN or other labs like that, turns out that there's actually 3 families of quarks. They're called the charm and strange, top and bottom. Physicists have a weird sense of humor, so don't read anything into that. It's just that we like to keep ourselves entertained. So, and then there are leptons, which are the sort of the extended family of electrons, electron, mu, tau, and 3 families of neutrinos. So this is pretty amazing, okay? It's 12, and we can explain all of this. there's just one missing ingredient at this point, which is the interaction between stuff. So stuff does not only exist, but interacts. So for example, when I'm talking to you, you see me, and you see me through light. Light is the electromagnetic interaction, and that's mediated by photons, okay? So we also need photons here. There's a particle that keeps together the nuclei of atoms. That's called the gluon. Again, it's physicist humor. And then there are other particles called the W and Z bosons. They're responsible for some kind of radioactive decays, and the gravity, because there's also gravity in the universe. And that is pretty much the standard model of particle physics. So if we were beings confined to Earth, this is how we would explain, this is how we would answer the question. What is the universe made of? The universe is made of this. So now, do I stop, go home? No. Unfortunately, or fortunately, if I take the point of view from the universe, things look very, very different. And we have to go back in time a little more once again. So let's go back to our friends Newton and Galileo. So they've made many contributions to science, but one of the ones that is relevant here is that they asked themselves, is the universe made of the same stuff and governed by the same laws as Earth? So Galileo's observation of the sunspots, or the moonspots, he called them, or the phases of Jupiter, moons of Jupiter, they all showed that the heavens, what they called them at that time, were not uncorruptible. They actually changed in a similar way as Earth changes with the weather. We change, we age. And Newton's contributions are, of course, too many to name, but the one that I'm interested in right now is that his fundamental insight was that the same law of gravity that describes the fall of an apple also describes the orbits of the planets around the sun. So it's a unified theory of gravity that shows the laws of nature are the same on Earth and in space, on Earth and in heaven. Okay. So these two contributions together showed us that there was some similarity to what made Earth and the interactions between the stuff that makes Earth and what makes the universe and the interactions that take place in the universe. So we have to take now one step forward to the Pink Floyd. You have seen this before. Eh? So if you shine sunlight through a prism, you'll know that, you've probably seen this before, sunlight contains all the color of the rainbow. It contains many more, but the colors of the rainbows are the ones that we can see with our eyes. And those are interesting for us because spectra are really the fingerprints of atoms. This is a detailed spectrum of the sun, and you can see some black shades there. So on top of the rainbow, which is light of all the colors, there are some missing colors, very specific colors that are missing. Those very specific colors are bits of light, photons, that have been absorbed by atoms in the atmosphere of the sun. And every atom has its own very specific fingerprints in the same way as you can identify who committed a crime by looking at the fingerprints. By looking at the spectrum, any physicist can tell you what are the substances that are present in that gas or whatever substance is in front of that light. And so this is how we identify the composition of things outside of Earth. And this has been done, and actually this is how the element helium was discovered. The name comes from the sun, helium. And it turns out that stars are made of exactly the same stuff as Earth. So this is the chemical composition of the sun, and you can see there's about 3/4 of it is hydrogen, 1/4 is helium, and a tiny sliver is all the other elements. And if you zoom in on that sliver, it's mostly oxygen, carbon, iron, neon, so on and so forth. But these are exactly the same elements that we saw in the periodic table, exactly the same elements that are in your chemistry lab, exactly the same elements that you can describe with the particles of the standard model of particle physics. Now, there's one little interesting twist here, which is the so-called mystery of universal helium abundance. So imagine that you had a very precise instrument, and you were walking around campus, and every person you meet with a cup of coffee, you measure exactly the amount of coffee, milk, and sugar in their coffee, okay? So normally you would expect something like this. Some people like their coffee black, some people put more milk. There's a range of things. Imagine instead that here at UCLA campus, you find something like this, that everyone seems to have exactly the same amount of coffee and milk in their cup. Maybe the amount of sugar changes, but everyone is exactly 3/4 coffee, 1/4 milk, and trace amounts of sugar, 0 from small amounts. What would you infer? Now, raise your hand. This is a real question. Can anyone answer this question? What would you infer if everyone had exactly the same amount? Andrew. So Andrew is saying they're all made in the same place. They all come from the same source. And so this is exactly what happens when people start measuring the abundances of stars. The difference is that instead of coffee and milk, it was hydrogen and helium. All stars have about 3/4 hydrogen and 1/4 helium, with a small amount of sugar, and sugar are all the other elements, carbon, oxygen, and so on. And so then, as Andrew taught us, probably these stars all come from the same place. Okay, so where do they come from? Well, they come from the Big Bang. So it turns out that the universe was not always the same. The universe has evolved, and it's about 13.7 billion years old. And when it was very, very young, it was also very hot and dense. And it had such a high density and temperature that it acted as a fusion nuclear reactor. So the universe, in the first 3 minutes, was hot enough, like a hydrogen bomb, that it was able to fuse elements into hydrogen, helium, and lithium. Then what happened after that, after the first 3 minutes, is that the universe became too cold and not dense enough, and neutrons decayed. And so there was not enough material to continue the fusion reaction. And so the fusion reaction stopped. And if this had been the end of the story, we would live in a very boring universe. Actually, we would not live, because there could be no life with just hydrogen, helium, and lithium. You need carbon for life. So we have to wait a few billion years, and you can see there, first particle, first nuclei, first light, first stars. When the first stars form, about a few 100 million years after the Big Bang, stars are also hot and dense enough that they can resume the nuclear fusion process, and they form all the other elements. So this is an example. These are stars. This is a star-forming region on the right called the Eagle Nebula. This is like a stellar nursery where gas is transformed into stars. And inside some of those stars, there are reactions like this one. This is the triple alpha reaction that transforms helium into carbon. And we care very much about this, because organic chemistry, the base of our life, could not exist without carbon. Okay. So stars, during their life, form these elements, and some of other elements are formed at a star's death. Okay, when a star detonates in a supernova, some other elements are formed, and then these elements are dispersed into the interstellar medium, interstellar gas. Eventually, some of those elements make their way to planets like the Earth, and eventually to humans. So the recipe for humans is really stardust and Big Bang leftovers. So if you look at the recipe, if you want to write a cookbook for humans, you say, we are 65% oxygen and 10% hydrogen, because we're mostly water, right? So oxygen and hydrogen is water. The hydrogen comes from the Big Bang. The oxygen comes from stars. And then we have other stars, other things like carbon, nitrogen, and so on. And those all come from stars. OK, so is that it? No. There's something else coming up. Now it gets really interesting. OK, so I have to give you one other piece of information about astrophysics. So there's many terms that people sometimes use liberally, but I think I should define them. The universe is organized into stars. Stars are found usually in star-forming regions, or like the Eagle Nebula on the left. Star-forming regions are found inside galaxies, like the galaxy that you find here, and many times galaxies are found in clusters. So there's a whole hierarchy. That's a picture of the sun, which is pretty big to begin with. Galaxies can have 1,000 billion suns, and clusters can have thousands of galaxies inside them. And then there are, of course, superclusters and so on. It goes on and on and on and on. Okay, so this is how the universe is kind of organized. And we have to take a little time travel here to 1937. In 1937, this astronomer here named Fritz Zwicky, and you can see it's a pretty, apparently he looked like that. I never met him, but he did look like that. He made a very interesting observation. He was looking at galaxies in clusters, and he started measuring the velocities of the galaxies in clusters. And he found that galaxies move too fast. What does that mean? Okay, I have to make a little experiment here. Hopefully I don't kill anyone. So this is a softball, so hopefully. So imagine you have this flying around my head like this. So if I make it go faster, the tension on the rope increases. Okay? So the faster the ball orbits around my hand, the higher the force that needs to keep the ball orbiting. And so if you measure how fast galaxies are moving inside a cluster of galaxies, you have a measurement of how much gravity there is. And if I know how much gravity there is, I know how much mass there is. Kind of like if I jump like this, I can, in principle, figure out how much mass there is in the Earth. Then what he did is he compared this mass to the luminosity of all the stars in this cluster. And assume that all those stars are like the sun. From the luminosity, you can infer how much mass there is in stars. And it turns out that there's way, 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 way more mass than the mass in stars. Like 100 times more, or maybe 1,000 times more. But Zwicky was kind of weird and cranky. I don't know why. Nobody really paid attention to this. The tide really turned in the 1970s, where new observations, led by Vera Rubin and others, of galaxies showed a similar thing, that galaxies rotate too fast. So it's the same idea, galaxies rotating, and from the rotation speed, you can infer how much gravity there is. And then you can compare that with the mass you see, and it turns out that is much more. And more than that, you can see that the gravity extends way beyond the visible part of a galaxy. So this is, you might have heard about this, Kepler's third law. Have you ever heard about this? The law that tells you how planets go around the sun, So the planets that are closer to the sun go faster, the ones that are further out go slower. It holds for dwarf planets as well. Pluto is fine. So if you plot their speed versus distance from the sun, it goes down. So that's kind of what you expect for a galaxy, that when you reach the end of the galaxy, the orbital velocity should be decreasing. Instead, what Vera and others saw is that the rotation velocity beyond the visible part of the galaxy does not fall off as you would expect, but keeps increasing for many, 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 many thousands of light years. So this is clearly showing us that there is something there, some mass, some stuff that we cannot see. And so the name came, it was called dark matter. Now, I've been told to point out that dark matter does not imply anything sinister. It's not a conspiracy of any sort. It's just a sort of naive attempt of the astronomers to convey the fact that it does not interact with light. In fact, I personally prefer to call it transparent matter, but dark matter seems more exciting, so that's a standard name that people have for it. Okay, so now we've discovered there's this new thing called dark matter. Okay, so where and what is this stuff? Like, for example, it could be that it is just normal elements that we just don't see, right? It could be that it's helium there and we don't see it. Here comes to our assistance a technique called gravitational lensing. Okay, so I have to take you back to kindergarten. As we all learn in kindergarten, gravity bends space-time. So if you have, this is a representation of the solar system. The sun in the center of the solar system is curving space-time. So light rays don't travel in a straight line. They actually go around, oh, thank you. Higher powers, thank you. So they go around curves like that. So if I'm on Earth and I'm looking at two distant stars close to the sun, the apparent position of the stars will not be the same that I would see in the absence of the sun. This is because the gravity of the sun bends sunlight. It bends light, every form of light. Okay, so if I go to galactic scales like this one, and I'm looking, this is the Hubble Space Telescope, I'm looking at a distant source behind a very massive object, like a galaxy. The light bending can be so much that I can see more than one image of the background source. In this case, I see 4 images. So the picture you see on the right is what I see from the Hubble Space Telescope. There's a yellow thing in the center that is the foreground galaxy, and 4 images of the blue background object that have been created by this gravitational lens. It's called lensing because it turns out that it's exactly the same physics or the same equations as normal lensing, like the one that governs my glasses. Or in this case, it turns out the stems of wine glasses have almost exactly the same optical properties as galaxies. Someone designed wine glasses to match galaxies. I don't know why they did that, but it turns out to be the case. So if you hold a wine glass, make sure it's empty. If you hold the wine glass like that in front of a source of light, you can produce the classic configurations of gravitational lensing. You can produce Einstein rings, double 2 images, 4 images, and so on. So why is this useful? This is useful because it allows us to see mass or stuff not directly, but through the distortion that it imposes on background sources of light. And this is one of the most beautiful examples. It's called the bullet cluster. Okay, so this is an image taken with the James Webb Space Telescope. And in pink, the glowing pink, is the X-ray light that comes from hot gas. This is mostly hot hydrogen that is so hot that it emits in the X-rays. And you see that funny shaped object there that looks kind of like a bow or something. And I put there a picture of a jet breaking the sound speed because that's kind of what's happening here. So this is a collision between 2 clusters, and they went through each other in the plane of the sky. From the shape of that shock and the geometry of that shock, we can tell that they went through each other at about 2,000 kilometers per second. I'm afraid I have to translate this to about 1,000 miles per second. Per second, okay, not miles per hour, miles per second. And blue, what I show in blue there is the mass. And the mass is identified by the distortion it imposes on the background universe. And you see what's happening here. The mass is displaced from the atoms. The atoms are in pink, and the mass is in blue. And so what happened here is shown in this little movie here, where you see the 2 clusters collided with each other, and as they collided, the atoms, kind of like if I throw 2 buckets of water at each other, the water collides with itself. But the dark matter does not. Dark matter does not interact electromagnetically. And so it goes through. And so this cosmic collision separated for us the atoms from the dark matter. And this cosmic collision demonstrates visually that the dark matter cannot be atoms. There are many other reasons, many other observational facts that tell you that dark matter cannot be atoms that we just don't see. But this is the most visually compelling that I can find. And so we've established that dark matter is its own thing, and It probably does not interact very much with itself, certainly does not interact with light, and probably interacts with very little also with ordinary matter. And this is why it's so hard to see on Earth. Okay. I want to show you then, if I now were to give you dark matter goggles and you could see this dark matter, and you were able to take flight and fly through the universe, you would see something like this. The universe would look like this to you. This blue is the dark matter, and this is what we call the cosmic web. There are these filaments of dark matter that they cross each other occasionally, and these brighter points are the highest density of dark matter, and within those, that's where galaxies form. And within the galaxies, that's where the planets are. And where the planets are, that's where we are. Okay? So we're one tiny speck here in one of those little points. So this is kind of like the idea. Now there's one more surprise. So as if this was not strange enough, there's one more surprise. So we're known for a long time, at least for the past 20 minutes, that the universe is expanding. Okay? And so what happens is that the universe expands, and now what we would expect, I'll have to use this prop, high-tech prop again. Imagine that I throw this up in the air. What's going to happen? If I throw this up in the air, it's going to come back down, most likely. If I throw it very hard, faster than a speed that is called the escape speed from Earth, it's going to keep going forever, but it's going to slow down. So that's what you would expect for the universe in a normal situation, where the universe expands and it just slows down. Whether it slows down enough to collapse into a big crunch, or whether it goes forever, that's another question, but we would expect it to slow down anyway. The big surprise that was discovered about 30 years ago is that the universe is accelerating. And the equivalence here would be that if I throw this ball up in the air like this, it accelerates upwards. It goes faster and faster upwards. So this is very unusual, very strange. There's no classical analog to this. It's something that only happens in Einstein's theory of gravity. So no, I will not even try to explain to you why this happens, primarily because I don't know, and nobody knows, but this is a very strange fact. And this was actually named dark energy by one of our colleagues, Michael Turner, and the idea is that we know it's not stuff because it doesn't slow down the expansion. But it behaves kind of like energy. It's invisible, so dark energy. That's all we know about it, more or less. Okay, so let me try to wrap this up. What is the universe made of? So this is a nice summary as far as we understand it. So a very small, this is the cosmic pie, we call it, summarizing the composition of the universe. And I put on the same diagram stuff and energy because of Einstein's equation allows me to do that. So a tiny amount is light, radiation. Then there are chemical elements other than hydrogen and helium, small fraction. Neutrinos, those cousins of the electrons. Stars are just 0.5%. Helium and hydrogen gas, 4%. But then 25% is dark matter and 70% is dark energy. And this is what my colleagues and I are trying to find out. What is 95% of the universe? We know it's there. Unless we got something completely wrong, there's no way in which these things have to be there, but we don't know what they are. So the first open question that we're working on is, what is dark matter? And there are many ideas here. Here are two pictures. One is called cold dark matter, one is called warm dark matter. Cold is kind of like ice. You can think of particles that are not moving very fast and form little clumps. And so you can see there's lots of clumps in this picture here. And warm is more like water, where particles are moving around and they don't really clump as much. You can see the picture on the right is much smoother. Those correspond to potentially new particles. And in fact, if you ask any theorist, they have hundreds of possible models for what dark matter could be. There's certainly no shortage of it. And what we're trying to do in my research group is we're trying to figure out what it is. And we use a strange technique called flux ratio anomalies. I will not explain what it is. we tried to measure the properties of dark matter, and so far, our results seem to favor the cold dark matter hypothesis, something like a very massive cousin of the neutron that is stable. Something like that could be the explanation. There are hints that dark matter could be interacting with itself. That would be a completely new regime, but we don't know for sure that. Of course, the dark side, as we call it, could be a complete equivalent of the luminous side with its own interactions, with its own particles, and so on and so forth. We're just trying to figure it out, but it's dark, so the only thing we have to investigate this is gravity, because it's the only interaction that we know it has. And the other thing is, what is dark energy? So whereas in the case of dark matter, we have hundreds of theoretical ideas as to what it could possibly be, dark energy is much harder to find compelling theories for. And so I did what every respectable scientist does. If I have to show you a picture of dark energy, I went to Google, and I Googled it, and this is what I found. So it's a plant nutrient, and it says it stinks, but it rocks. So I don't think it stinks, probably doesn't, but it may rock for sure. And so what are we trying to do about dark energy? So the way we're trying to tackle this is to use a technique called gravitational time delays. This is a little esoteric, but what it allows us to do is measure very accurately the expansion history of the universe. And measure the expansion history of the universe is kind of like measuring the trajectory of this ball as I throw it. And that tells me about the gravitational field and what is causing it and so on and so forth. And something very exciting happened in the last few years. There seemed to be some indication that dark energy is not the simplest form, which is something called the cosmological constant that Einstein introduced 100 years ago, but maybe something a little more interesting. So this is pretty much an open question. We don't know the answer to this, but that's part of why we love what we're doing, because we don't know the answer. And so these are all the people that are working with me on this, and I will take questions now. Thank you.
Thank you, Tommaso, for a great lecture. So I'm here to invite you to ask Tommaso questions about what our universe is made of. So we have a hand up in the back there. Yeah?
Fantastic. So can dark matter be seen only on really large cosmic scales or detected only there? Is the room not full of dark matter right now? And why do we not see any effects on the solar system and planets which seem atypical?
Yeah, so dark matter is everywhere, obviously. It's here, right? It's here with us, right? But the density here is much higher than the average density of the universe, right? Because the Earth is a very overdense place. So the gravitational effect of dark matter is not measurable on Earth. It's not measurable on the scale of the solar system either. But dark matter is in principle detectable in Earth-bound laboratories. In fact, some of my colleagues here in the department are doing amazing experiments to try to detect it via its interactions with normal matter. The difficulty there is that it relies on it interacting with normal matter, which we don't know if it does. So decades of search, they're called direct detection experiments so far, have only allowed us to put upper limits on how much it interacts with normal matter. So I would love to see a direct detection. That would be fantastic, because it would prove that it would tell us something about the particle. But so far, the evidence is purely based on astronomical observations on scales that are large enough where the effect of dark matter become important.
Thank you for your talk. It was wonderful. In popular science reading I've encountered the hypothesis that the dark matter is so-called primordial black holes created at the Big Bang. Could you comment on that theory?
Yeah, so that is one of the possibilities. So it is possible that in the early phases since the Big Bang, through a variety of mechanisms, something called primordial black holes could have formed, and those could act as dark matter. So we have observational limits. We can rule out many parts of the so-called parameter space, like many masses. So for example, my own observations tell you that dark matter, no more than 17% of dark matter in a certain mass range could be made of primordial black holes. Observations by other people, including Professor Gusenko, rule out other parts, but it's certainly one of the possibilities that is dark matter could be made in part or completely by black holes that are left over from the Big Bang.
Do we have any further questions?
Yes.
Yes. Oh, here in the middle, red shirt.
Can you comment about the Hubble tension? And also, I read some articles saying that dark energy is not constant throughout the life of the universe.
Yeah, so two important questions. Thank you for allowing me to expand on what I was saying about something very exciting that happened in the past few years. One is the so-called Hubble tension. So if we measure the expansion rate of the universe directly, or if we predict it from observations of the early universe, the two results appear not to match. And if this is correct, it could be an indication that our understanding of the universe expansion history is not correct. And one of the ways to solve it is to introduce something that people have called an early dark energy, which would be another kind of dark energy, yet another strange substance. The second thing you refer to is a measurement by the DESI experiment that showed that dark energy does not seem to behave like the cosmological constant. So when Einstein in 1929 found out that the universe was expanding, before that, he introduced the cosmological constant to try to create a static universe solution because he was a firm believer in the fact that the universe should be eternal. And then they discovered the universe was expanding. He got rid of the cosmological constant. And then the cosmological constant became popular again because it's the simplest form of dark energy you can have. It's just a constant that you add to Einstein's equations. Pretty simple. But it turns out that the observations by DESI, if they're correct, show that it's not that simple thing. It's something that changes with time. It's not just a universal constant. That the jury is still out is a very complicated measurement, but if that's true, that's very exciting.
We had a question here in the front row.
Thank you very much for your lecture. How do we know, in fact, that there was this Big Bang?
How do we know that there was a Big Bang? So there's many ways in which we know that. And of course, the knowledge of science is always like, this is our best scientific hypothesis, okay? That's how we know things. But I would say my favorite line of argument is Olber's paradox. So tonight, when the sun sets, look at the sky. The sky is dark. And so that it tells you that the universe cannot be simultaneously eternal and infinite. Because if the universe was both eternal and infinite, any line of sight will sooner or later intersect a star. And so the entire sky should be as bright as the surface of the sun. So that the fact that the night sky is dark tells you that the universe must be either finite in space, so it has an edge, or infinite in time. It cannot be finite in space because it would be unstable, it would collapse over itself. So the solution we have to Olber's paradox is that it must have had a beginning. So if in any direction, you run out of time. So if you look more than 13.7 billion years away, light billion years away, there's no star because there was no universe. And so most of the sight lines are dark because the universe is not eternal. So the night sky already tells you that the universe is not eternal.
Thank you.
My question is more, I think, philosophical than scientific. But if we're saying that the Big Bang occurred at a point in time, we're bound to ask ourselves what was before that. What was before, if we're giving a point in time, what was before that? And my other question is, what was banging in the Big Bang?
Okay, the second part is fun, is the easiest one because there's no sound, so nothing was banging. So the name was derogatory at the beginning. The critics of the Big Bang theory called it Big Bang to make fun of it, so you shouldn't read much into the bang. But, so as my wife taught me, there's a beautiful quote by St. Augustine saying, that you cannot ask the question, what was there before time? Because there's no before time. Time is what introduces before and after. So you cannot ask the question, what was there before time? There was no before. It's the beginning of time.
Tommaso, no one will sleep tonight. Let's see. Okay.
You mentioned when showing the bullet cluster image with the dark matter on the outside and regular matter concentrated on the inside, that this is because dark matter doesn't interact electromagnetically. Is
Right.
that, I guess, does normal matter interact very electromagnetically
Yeah,
when it's colliding galaxies to cause that effect? Or
You
is that
see my
because-
shoes?
Yes.
My shoes are interacting with the floor. And that's why I don't go through the floor. So that's the same thing that happens to the colliding clusters. The atoms collide with each other. It's the same way as my shoes interact with the floor, more or less.
Thank you.
May I?
It's hard for me to see. I'm
Maybe
sorry.
I can ask quickly. Thank you for your talk. So I wonder if you could give us a couple of examples how James Webb and gravitational waves are being used to investigate these questions about dark matter and dark energy.
Yeah, so gravitational waves, which is a phenomenon that has been recently discovered, potentially have a way to help us a lot in this kind of question, because gravitational waves have some features that can be used to measure their absolute distance to the source of the gravitational wave, and you can turn that in principle to a measurement of the expansion history of the universe. So we're not quite there yet in the sense that we don't have enough of those systems known with sufficient precision and so on and so forth. But in principle, we can use, they're called gravitational sirens, to learn about the expansion history of the universe. Yeah.
Okay, thank you. Great.
Sorry?
Sure.
What about James Webb?
What about it?
James Webb.
I've been using it all the time. We use it all the time for this.
So I think the question was specifically, what new aspects of the universe are you learning from the observations made from James Webb? I'm not sure if I have that right, but
Well, for example, much of the evidence in favor of the Hubble tension comes from James Webb and Hubble Space Telescope observations. Some of the evidence that I've shown you here comes from James Webb and Space Telescope observation. So they have a lot to say about all these topics, yes.
Thank you for your lecture. My question is, even if we haven't built it yet, is there a possible way to collect and like somehow study dark matter? And if so, like what experiments could we possibly do on it?
So there are two ways. One is the direct detection experiments that I've been alluding to. The other one, in principle, if it's a particle, you can create it in accelerators, kind of like the same accelerators that were used to study the standard model of particle physics. You could imagine creating some of these particles in accelerators. This has not happened yet. We have not seen them, but that's in principle a possibility. Yeah.
Okay, thank you.
Hi. Sorry, am I interrupting? No. Okay.
Go ahead.
Thank you so much. Amazing talk. And I just was fascinated by you show there is a cloud of visualization of how dark matters when the two clusters collide. So do you guys ever draw a map like how dark matter is distributing in our galaxy, in the solar system? Do we live surrounded by dark matter, or is it still really far away from us?
No, it's everywhere. It's going through me right now.
But it's not homogeneous.
It's not?
It's not homogeneous.
It
in the
looks
galaxy.
like this. So you know this movie that I showed? It kind of looks like this.
Do we live in the dot, or do we live in the dark?
We live in one of those little bright dots somewhere.
Thank you.
So maybe I'll follow up on that. So you showed a plot of how you would expect the fall off of the velocities around the edges of galaxies would occur if there were no dark matter versus what was observed. So from plots like that, what can you tell about the distribution of dark matter?
Well, you can tell, we can measure pretty accurately how it's distributed. And by comparing that to cosmological numerical simulations, for example, we can set some limits on how much it interacts with itself and how much it interacts with baryons or with
I was curious about, what specifically do you learn about the distribution from plots like that?
You learn a spatial distribution to very high precision.
Which is?
Which is then related to its properties, right? Because if it's, say, relativistic, it won't have a certain distribution. If it's non-relativistic, it would have a certain distribution.
Okay.
You talked about the quarks, the very basic, actually, components of the universe. So what is beyond that? What are the quarks, bosons are made? Are they real particles? Are they, if you crack them, is there something smaller than them?
Then quarks?
Yeah, then quarks. If you crack the quarks, the smaller particles, are they real atoms, not crackable? Or what is beyond that?
As far as we can tell, that's where it stops. But you never know. We've been surprised before. So.
Yes, hello. I'm wondering if you could speculate here for us, if you find out what dark matter and dark energy are, what it might portend for the future free source of energy or other dimensions of reality, or most importantly, extraterrestrial life.
Okay, that's a long one. Okay. Okay, so I would say, it's kind of like when Democritus was doing his thinking. I don't think he was thinking about my iPhone. So it's kind of like probably there's the same level of connection there at some point, but I don't know what it is. In terms of life, the story I told you is how we understand life, right? So life is connected to the Big Bang and the stars and so on and so forth. The role that dark matter and dark energy play in all of this is making the universe possible. So if you don't have dark matter, you don't form structures. If you don't have dark energy, the universe does not have the right age. It becomes too young. And so you can think of them as being the conditions that enable life. And in fact, there are theories, so-called multiverse theories, where you have many universes, and each one of them has random different constants. But if you get the wrong balance of dark matter, dark energy, and so on, you don't get the time to form stars, you don't get the time to form planets, you don't get the luxury of a star living 4 billion years with a planet nearby for life to evolve. And so you can think about them as being the stage for, if you're interested in life, they're the stage for life.
Can I just ask a follow-up question? Could it portend a whole new set of physics for us?
Sorry?
Could it portend a new set of physical laws, or does dark matter and dark energy conform to what we know?
One of the ways in which people try to understand this is by changing the laws of gravity. So there's a whole new field of modified gravity where people are trying to find theories of gravities that are sufficient to explain the universe without dark matter and dark energy. There's been no successful attempt that I'm aware of, because Einstein's theory of gravity is very good, and also observations like the bullet cluster make it very hard to just play with gravity. It looks like there really is something different. But never say never. Maybe someone clever comes up with a new theory of gravity that gets rid of dark matter, dark energy. Hey, that's great.
Hey, thanks for the talk. I was just wondering, do we know if dark matter can interact with black holes? Can a black hole suck up dark matter into it?
So black holes don't suck. Okay. Black holes are awesome. So black holes are gravity like any other. So black holes and dark matter interact gravitationally all the time. And in fact, dark matter can fall into black holes pretty much as other kinds of matter can fall into black holes, and so on and so forth. So from the point of view of gravitational interaction, dark matter and black holes are just like regular matter. There's nothing special about them.
Okay. Cool, yeah. All right.
Thank you for the lecture, Tommaso. This is not my specialty, and I am grateful I don't have to take the test. But I thought at one point, I'm probably confusing things, that there was no time really before the Big Bang. Although I thought early in the lecture you said the Big Bang takes place 3 minutes or 3 seconds after something?
No, so in the first 3 minutes after the Big Bang, that's where hydrogen, helium, and lithium were formed.
Okay.
After the Big Bang.
Okay. And how do we know 3 minutes?
How do we know? No, that's a beautiful question. We do know. So there's something called Big Bang nucleosynthesis, which is one of my favorite pieces of physics. So you can take what you know about nuclear reactions and nuclear physics and calculate from first principles what should be the abundance of special isotopes of hydrogen called deuterium, tritium, and so on. And then you can go and measure them, and they match exactly what you predict. And that tells us when it happened, and also tells us the abundance of normal stuff at that time. So we have pretty direct evidence of what happened in the first 3 minutes.
Thank you so much for your lecture. From my understanding, there's a theory that dark matter is composed of weakly interactive massive particles that share similar properties to neutrinos. Could you elaborate a little bit on this theory?
Yeah, so this is called WIMPs, and WIMPs are probably the leading candidate. When I refer to some sort of like bigger cousin of the neutron, that was my sort of clumsy attempt to describe a WIMP. So those would be massive particles with very big mass, no interaction, very boring. That would be the leading candidate, and that's pretty reasonable observationally. Another possibility is cousins of the neutrinos that we call sterile neutrinos. Those would be a little less massive, more similar to the warm dark matter I was showing. So there's plenty of ideas. So there's no shortage of them. I hope that we can pin down which one of these ideas, if any, is the correct one.
Okay, let's take one more question before ending.
Tommaso, hi. Thank you for a phenomenal lecture. My question is, we know that 5% of the universe was definitely created after the Big Bang. There's 70% dark energy and the 25% dark matter. They were then also created after the Big Bang?
Okay, so that is an interesting question. Dark matter, certainly. I mean, we know it's been around for a very long time. Dark energy, we don't know. So depends. And if it's a property of space-time, kind of like the cosmological constant, it was always there. If it's dynamical dark energy, maybe it started at a certain point. We don't know why. So it manifests itself only a few billion years ago. Earlier on, it doesn't seem to be very important, but maybe it was already there. We really don't know.
Thank you, Tommaso, for a wonderful lecture.